Think of any number. Chances are it's built out of smaller, more fundamental blocks. But the blocks themselves appear to obey no rules at all. This is the paradox of prime numbers, the unpredictable foundation of our entire mathematical universe. A prime number is an integer greater than 1 that can only be divided by 1 and itself. 7 is prime because it's irreducible. 9 is composite because it factors into 3 times 3. This scrolling number line shows how those prime building blocks scatter. Sometimes they clump together as twins, like 11 and 13. Other times you have to cross massive gaps of dark composite numbers just to find the next one. There is no obvious sequence. It is a strange contradiction. The mathematical atoms that build every other number exist without a universal rule governing where they appear. This grid shows our oldest method for finding them. For over 2 millennia, we relied on the Sieve of Eratosthenes, a process of systematically crossing out the multiples of 2, then 3, then 5, until only the primes are left standing. While this works for the first 100 numbers, it fails at scale. Hunting for primes with millions of digits via manual filtering is a computational task that would outlast the universe. However, patterns emerge when you change the geometry. By wrapping the number line into this spiral, the primes begin to align, forming distinct diagonal lines across the grid. This Ulam spiral suggests that primes aren't purely chaotic. There is an underlying structure waiting to be mapped. For centuries, mathematicians hunted for a single arithmetic equation, a shortcut that could pinpoint the exact location of the next prime without the need for sieving. This is Leonhard Euler's polynomial from 1772. By taking n squared, adding n, and adding 41, it produces 40 consecutive verified primes. At n equals 40, the pattern breaks. It outputs 1681, which is 41 times 41. The local rule collapses into a composite number. In 1964, C.P. Willens did develop an exact general formula for the nth prime, but it came with a massive computational catch. As this handwritten summation shows, Willens' formula relies on nested sums and factorials. To find even the 50th prime, a computer must process millions of iterations. A clean, predictive formula for individual primes remains a mirage. In this case, the mathematical cure of an exact formula is far more complex than the disease of testing each number manually. If pinpointing a single prime is impossible, we can instead look at their density. We can't say where the next prime is, but we can say how many primes exist within a certain range. This chart shows the prime number theorem. It illustrates how the frequency of primes predictably thins out as numbers get larger. It is a precise statistical law governing the macro scale. In 1859, Bernhard Riemann connected this statistical thinning to a mathematical landscape involving the complex plane. He found that zeros in his zeta function act as frequencies. Like musical notes, they dictate the exact oscillations of primes around their expected density. These zeta zeros provide an exact reconstruction of the prime counting function. Primes may look scattered up close, but they are bounded by a rigid analytical structure. In practical terms, there is a major difference between predicting a prime's location and testing a number to see if it is prime. While prediction is impossible, modern primality tests allow us to verify enormous candidates with extreme speed. This is the work of GIMPs, the Great Internet Mersenne Prime Search. They evaluate numbers tens of millions of digits long, using distributed computing to find the next probable prime. We have traded simple formulas for the raw power of cloud supercomputers and GPU clusters, running high-speed primality tests across 17 countries. Because we cannot predict them, humanity has engineered massive brute force architectures to find the next prime number by sheer volume. This local unpredictability secures modern digital life. It is the core mechanism behind RSA encryption. This diagram shows the one-way street of prime math. A computer can multiply 2 large primes in an instant, but factoring that product back into its original primes is so difficult that it would take a standard computer millions of years. This mathematical asymmetry protects your ATM withdrawals, private messages, and digital signatures. We rely on the fact that primes are easy to use but impossible to reverse engineer. We can map out their global frequency and test candidates millions of digits long. Yet no known simple formula can efficiently predict the exact location of the next prime. Primes are the fundamental building blocks of the universe. Yet they refuse to follow a simple path. Are prime numbers truly unpredictable, or are we just waiting for a deeper mathematical lens to see the logic?